Fire a fast projectile through air or water, and the fluid pushes back with a force that grows as the square of the speed. That one fact changes how the object slows. At low speed, drag is proportional to velocity, and the speed dies away exponentially. At high speed, drag grows as velocity squared, and the answer is completely different. We will solve for the velocity over time and watch it fade not exponentially, but as a long reciprocal tail. Picture an object of mass m launched at time 0 with speed v0 through a fluid of density ρ. Its cross-sectional area facing the flow is the area A. At high speed, the retarding drag force has magnitude 1/2 c sub d a ρ times v squared pointing opposite the motion. Bundle those constants into a single coefficient. Beta equals 1/2 c sub d a ρ. Let the object move in the positive x direction, so its velocity is simply v. Newton's second law sets mass times acceleration equal to the net force. Drag is the only horizontal force, so m dv dt equals minus beta v squared. The minus sign says the force always opposes the motion, steadily slowing the object down. Start from Newton's law, m dv dt equals minus beta v squared, and solve it by separating variables. Divide both sides by the mass and by v squared, then multiply through by dt. Every bit of velocity lands on the left, every bit of time on the right. dv over v squared equals minus beta over m dt. Now integrate both sides. On the left, the velocity runs from its initial value v naught up to v of t at time t. On the right, time runs from 0 to t. The integral of 1 over v squared is minus 1 over v. Evaluating between the limits gives minus the quantity 1 over v of t minus 1 over v naught. The right side integrates to minus beta over m times t. So we reach minus 1 over v of t minus 1 over v naught equals minus beta over mt. Clean up the signs. The two minus signs cancel, leaving 1 over v of t minus 1 over v naught equals beta over m times t. Add 1 over v naught to both sides to isolate 1 over v of t. 1 over v of t equals 1 over v naught plus beta over mt. Put the right side over the common denominator v naught, and it becomes 1 plus beta over m v naught t, all divided by v naught. Now flip both sides. The velocity as a function of time is v of t equals v naught over 1 plus beta over m v naught t. Define the time constant tau as m over beta v naught. In terms of tau, the result takes the compact form v of t equals v naught over 1 plus t over tau. The mass rides inside tau, so a heavier object slows more gradually. Look at the shape of this decay. With an initial speed of 20 meters per second, the velocity drops steeply at first, then bends into a long, slow tail that creeps towards 0 but never quite reaches it. This is reciprocal decay, 1 over 1 plus t over tau. Compare it to the low-speed case, where drag is proportional to velocity itself, not its square. There, the velocity falls off exponentially, as v naught times e to the minus t over tau. Early on, the exponential and the reciprocal look alike, but their tails part ways. The exponential keeps plunging, crushing the speed towards 0. The quadratic drag tail lingers, holding on to a small velocity far longer. Stronger drag while fast, yet a slower, fatter tail at the end. The fourth law dictates the decay law. Square the velocity in the drag, and separation of variables hands you a reciprocal. V of t equals v naught over 1 plus t over tau, with time constant tau equal to m over beta v naught. Notice the mass sitting right there in the time constant. A heavier object carries more momentum, so it takes longer to slow. Unlike the clean exponential of low-speed drag, quadratic drag produces a decay that starts sharp and ends with a long lingering tail. Same law, Newton's second law, but a completely different fingerprint in time. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.